Hi. So in this video we're going to look at another method of proof, and it's an indirect method of proving a statement. We call it proof by contradiction. So as you might have guessed, it involves a contradiction. So the steps are, we look at the statement, we assume a negation to be true. So for example, we'll look at example 1, prove by contradiction root 5 is irrational. So the negation of that statement is let's assume root 5 is rational. Now we know that not to be true because root 5 is absurd. Okay? So then what we're then going to do is we're going to do some algebra, and then we're going to arrive at a contradiction, which therefore means the initial assumption is false, which therefore means the original statement must be true. Okay? So for this particular example, which is a very common exam question, should this come up, what we're going to do is, so we're proving that root 5 is rational. If it is rational, that means it can be expressed as a fraction which has no common denominator between the numerator and the denominator. Okay? So A over B, where A and B have no common factors. If they had common factors, then it would simplify, okay? And it would just be root 5 equals A, so it would be a number. So that is the definition of a rational number, is it can be expressed as a fraction, A over B. If it's 10, it's 10 over 1. If it's 20, it's 20 over 1. If it's 5 over 2, it's still a fraction. Whereas a rational number, an irrational number can't be expressed like that because it's a recurring decimal. For example, a third. So now we're going to have some steps of algebra to prove that this is wrong. So we've got a squared equals b squared times 5. That means a squared is divisible by 5. So that little symbol there, however, written it is a squared is divisible, or 5 divides a squared. Now if you think about how powers work, if 5 divides a squared, therefore 5 must also divide a. Okay, so that means if 5 divides a, we can express a as some multiple of an integer by 5. So now we've ended up with 5k all squared equals 5b squared. Okay, so what we're going to do next, so we've also, firstly, let's re-establish, I worked out that a is divisible by 5, which is important. Okay, now let's get an idea of what b turns out to be. Okay. So I've actually ended up with a very, very similar statement. B squared equals 5k squared. Okay? So that means 5 divides b squared. So now I've ended up with 5 dividing b. But we've already got that. We know that 5 divided by a, 5 divides a, but now 5 divides b. So that means A and B have a common factor in 5. And there's a contradiction. I assumed root 5 is rational, such that root 5 equals A over B, such that A and B has no common factors. But I've just said that it must have a common factor. Contradiction. Therefore, root 5 is irrational. Okay? So that might take a bit of abstract thinking to understand that, which is okay, because it is quite complicated. It's very conceptual, but it'll eventually get there. Okay? So let's move on to example 2. Prove by contradiction that a plus b over 2 is greater than or equal to ab all square rooted. So let's first of all get the contradiction, or rather the negation of the statement. So there I've assumed that a plus b over 2 is less than ab. Okay, so now I've got to do some geometry to end up with a contradiction. Okay, so let's see what happens. So there we've ended up with a squared plus a plus b all squared is less than 2 squared times a times b. So let's see what then happens. So I've expanded the double bracket. I've taken the 2 squared ab over to the left hand side, which turned out to be 4ab, so it becomes minus 4ab. So now I'm going to get, if I simplify the terms, so now what I can actually do is factorize that. It's actually going to be very similar to what we started off with the a plus b all squared. It's going to be a minus b all squared if we did some trinomials. Now, if we think about what that means, I've written a minus b all squared is less than 0. A and b are integers, or rather they're actually natural numbers. If you square a number, it's going to become positive. Unless it's I, then it's going to become -1. But we're not dealing with imaginary numbers, we're only dealing with natural numbers. Natural numbers being 1, 2, 3 carried on. So there is no way, even if I have b larger than a and it ends up being negative, I'm going to square it and then I'm going to end up with a contradiction. There is no way that I can have a and b in the set of natural numbers squared in that situation that is less than 0. Therefore, contradiction. Giving us the indirect proof that a plus b over 2 is greater than or equal to the square root of ab. Proof by contradiction. If you see in the top right, I've written what those symbols mean if you're not sure what they are. The inverted a means for all, and then the weird e looks like in the set of. So if we look here, that means for all ab values in the set of n, the natural numbers. And if we look at the left, it is root 5 with the e a line through it in the set of whole numbers, q. So that gives us The e with the line through it is across, it means root 5 is not within the whole numbers. Okay? So, that's proof by contradiction.